Okay, so for our last talk of this little breakout session, we have Manami Roy, who's going to be talking about a classification of discriminant ideals.
Thank you, everybody, to sticking through the this session. And I'm going to talk about this. It's a joint work in like 2 different projects, but the classification I'm going to talk about, it's not complete yet. It's ongoing work. But first, I want to describe what is this discriminant ideal twins. Okay, so let's get into it. It's a talk about elliptic curves. I know we had 2 talks in a row about representation theory, and you would be expecting discriminant ideal twins are probably about representation theory. It's not. It's about elliptic curves. So let me get started with elliptic curves. So I'm going to look at the Wester's equation of elliptic curve. So you can basically start with any of this kind of implicit equation in x and y. And I want to define the discriminant. This delta is a discriminant, so I define the C4 and C6. All of these 3 invariants are, but you will not see that much in the talk. I will mostly talk about this discriminant, okay? And for elliptic curves, we want the discriminant to be non-zero. And so this discriminant has to be non-zero, and elliptic curves are projective curves, so you have to think about, oh, there is this point at infinity, but throughout this talk, you will not need it, we will not use it. But we're going to start with this elliptic curve. And then I want to talk about discriminant ideal twins. So I have to talk about discriminant ideals. What does it mean? And then I'll define the definition of that. So before that, let's look at an example of a elliptic curve. So this is not an elliptic curve, and this is an elliptic curve, right? It's a simple example. Now I want to define what is a discriminant, minimal discriminant ideals. So to do that, first I want to define it locally. So for any number field, k, I want to look at the elliptic curve over the number field, but then I want to look at the embedding of this number field in the completion, the periodic completion, which I'm calling as KP. And we view the same equation of the elliptic curve over that completion, KP. And we look at that elliptic curve and we call it a P minimal model if the periodic valuation of this delta, the discriminant of the elliptic curve, is minimal. Okay. And even if this curve, this minimal curve, is not unique, the valuation is going to be unique, and it's called the minimal valuation at that prime. Now, it turns out that for each prime P of this, for this particular number field, we can get this minimal model. We can get to a minimal model, which is like, we can get to a model which is K isomorphic to E, and it has this minimal discriminant, which we are going to call as delta P. And then we define the minimal discriminant ideal. So this is a thing for this number field. So it's an ideal, which is a product of this prime power, and this valuation is the valuation of this P minimal discriminant, which we are choosing, right? So we don't have to do all these things if we are thinking about Q or if you're thinking about class number 1. But since I want to talk about in general, so I have to remind you guys of discriminant ideals. What does it mean? Otherwise, we could have just taken the discriminant. Okay, so this is the discriminant, minimal discriminant ideal of a number field. But like I mentioned, that we are going through all this trouble because for a number field, it's not always, for any number field, it's not always possible to choose one equation which is simultaneously minimal at every prime. Okay, so one of the example I gave here is this example. This is the LMFDB level, where your discriminant of this elliptic curve is actually this one. So this is not itself is not a P minimal model, and you can try to make it minimal prime. You can do some kind of a isomorphism. You can do some transfer to make it minimal here, but then you will realize that it's not minimal at some other prime. So it's not simultaneously minimal at all the prime, okay? When that happens, in that nicest cases, we have a global minimal model, okay? So this is the definition of a global minimal model. In that case, this this discriminant ideal, which we define, that is actually a principal ideal and is generated by this discriminant itself. Okay, and those are the nicest cases like Q or class number 1. It happens. But I want to talk about in general, so you have to keep in mind that we are in general going to work with this discriminant ideal, not the global minimal model case. Now, to define the discriminant ideal twins, which is in the title of the talk, we want to define something called conductor. Maybe many of you have heard of conductor of a elliptic curve. Like discriminant ideals or discriminant itself, conductor is also a very important quantity which looks at the complexity, arithmetic complexity of the elliptic curve. Okay, so we have few reduction types so it's called when a elliptic curve is a bad at a particular prime. Okay, so it has good reduction if the valuation at that particular prime of the discriminant, or think about this minimal discriminant at that prime, is 0, and it has, I should have called the multiplicative before. I usually define good, then multiplicative, then additive, but I switched them here. So it's multiplicative if this condition satisfied and additive in this condition satisfied. So multiplicative in a way is the middle, and additive is the worst bad reduction can happen, right? And this is the definition of a conductor. I'm defining the conductor of any over any, also ideal. In general, you can think about it as a number if you're doing, but again, we're doing it over number field. So it's an ideal which is defined like this. And this valuation right here, this FP is actually this valuation right here. This, FP is not this valuation right here. FP is a constant which can be either 0 for good reduction, it's 1, or this quantity right here. And this delta, we also have a bound for this delta. This delta is 0 when P does not divide 6. So that means the maximum, in the bad reduction, maximum conductor can be, conduction valuation can be 2. Otherwise, there is a bound for this, right? So it cannot be anything. There is a bound, but it's still hard to work with them, especially the prime P equals to 2. We'll see that. So this is the definition of a conductor. And finally, we are defining what is a discriminant ideal twins. So for any number field, the E and E prime, there are 2 elliptic curves. They are defined over the number field. And we call them discriminant ideal twins if they have the same discriminant ideal and same conductor. Okay. And we'll say that they are discriminant twins if they're this minimal discriminant at each prime, they're actually same. Okay, then we'll say that these are discriminant twins. But we are first going to look at both of the classification we are doing at the simultaneous. They are anyway discriminant ideal twins, right? So let's look at a definition of isogeny, because we are going to do this classification for elliptic curve which are isogenous to each other. So in that case, you have a morphism from one elliptic curve to the other, and the kernel is finite. We are going to consider n isogeny, or 2 elliptic curve are n isogenous if this kernel is the cyclic group. Okay. So in the case of isogeny, people might think that it's really complicated, but it's really not. You can write the map actually in terms of some rational function. I'll give you an example for it. So it's not always hard to think about isogeny. You can write them and think about the isogeny. One thing to notice is that 2 isogenous elliptic curve will have the same conductor. So that means when you are studying discriminant ideal twins for isogenous elliptic curve, we just need to think about when the discriminant ideals are going to be same, because conductors are anyway same. So here is an example. I promise that it's an example for 2 isogeny, and you can see that this is given in terms of some kind of rational function. Okay, now let's come to the question of what we are studying. I mean, I already mentioned we are going to classify the discriminant ideal twins, but we are specifically doing it for the isogenous elliptic curve. So you want to ask this question that if you start with two isogenous elliptic curve, particular isogeny degree, then they are non-isomorphic, then what happens to their when they are going to have the same minimal discriminant ideal? Now, after I bored you for so long talking about this, you will be asking why? Why should I care about this, right? So let me give you one motivation of why we should care about it. So there is this one problem which is really interesting. It's about finding a quotient or finding when an elliptic curve in an isogeny graph or in an isogeny class, finding this optimal quotient for that. This discriminant ideal twins, they serve as an obstruction. Like these are the think about, they are the only obstruction you can have if you want to use this method, this modular parametrization method by Shimura curve, which is introduced by the Rivett Takahashi to find the optimal quotient. So it's easy to find the isogeny degree, which is invariant under isogeny, but it's not easy to find this optimal quotient, which is also invariant under this isogeny. So to find this optimal quotient, it seems like computing this is going to be really useful. So it's like a baby step towards it. And finally, we want to kind of find an algorithm of finding this optimal quotient. That's the main goal. It's a far away future goal. Before that, we have to complete this classification. Okay. So let's start with the start of this work, which is this paper by Alison Dennis in 2018. This is, I think, one of the Omen in number paper. I forgot what was exactly the year was, but here she proved this, that if your isogeny class has size 2, in that case, at least if at least one of the prime has the multiplicative reduction, then it cannot be discriminant ideal twins. So if you have one prime multiplicative reduction, there is no chance of getting the discriminant ideal twins. And she also gave this complete list of what happens over Q if it has semi-stable reduction. That means at each prime you have multiplicative reduction. Okay, and this list is basically this few curve in LMFDB, and you can see that their discriminants are same. Actually, in this case, they're discriminant twins, not even discriminant ideal twins, they're discriminant twins, much more better. Now, what we want to do, we want to complete this classification in general. And first, we looked at the P isogenous elliptic curve, and then we are going to look at the composite degrees. Now we have to leave this semi-stable reduction case, and you have to look at in general for other bad primes, other bad reductions are happening. And we will also use the parametrization of these elliptic curves to do that. Okay, so this is kind of like what we are going to do in the next talks slide. This is the parametrization which is given by Alex Barrios. We are using it for this work. So this is for elliptic curve which has a certain isogeny degree. In this case, I'm considering the prime isogeny. Then they are, I'm also assuming the J invariants are not both identically 0 and 1728. In that case, these two elliptic curve in that isogeny class will be parameterized by these two parameters. D is the twisting parameter, and T is actually varying. And you can explicitly write down what is this thing is. So if you choose a particular T and D, it will give you an isogenous elliptic curve for this particular prime, right? So you are using this parameterization. So if you can do this question of classification for these curves, then that means you solve the problem for all the isogenous elliptic curves. So here is the first result. This is the work we started in SRNT1, rethinking number theory. Ali was the person who led this project. And we came up with this result that we can get a condition on this parameter T. And this is this really nice condition, which will tell you that when they are discriminant ideal twins. And they will be discriminant twins if further this T belongs in this OK, right? So there is this really nice condition you can figure out. Now, you can see that here the 2 is missing, right? I said 2 is a problematic prime. So so for the 2, what happens is one direction is true, the other direction is not true, right? So we are working on finding a converse statement of this, and we have to work a little bit more towards it. We also have a J invariant 0 and 1728 case. In that case, you see that only prime which matters is 3 and 2. 3 when J invariant is 0 and 2 is when 1728. And we have a condition for when it's going to be discriminant ideal twins. In this case, though, we cannot use the parameterization of Alex Barrios, which we stated in the previous thing. So you have to do it in a different method. But we also get a result for 0 and 1728, if you're thinking about it. Here is a list of all the p isogenous discriminant ideal twins over Q up to twist. Okay, so we see some of them probably you saw a version of it over Q where it's semi-stable. And this is the cases when, in all the cases when it has the isogenous discriminant ideal twin. Now, extending this work, we have continued working on it for p square isogeny elliptic curves. When p equals p is odd, basically, that means we have the genus 0 cases. So in this case, we will have p equals to 3 and 5. And we use the similar parameterization by Alex Barrios to get this result here. This is for 9. You can see again, we get an equation, we get a condition on this parameter t, which gives you when exactly this is discriminant ideal twins. And then we get a result when they're discriminant twins, right? And similar result for 25 isogeny cases. So I plan to talk about a technique, a little bit of the technique of the proof if I had time. I don't have time, so I'm not going to talk about it. So here, let me give you the list of p square isogeny cases. And these are these 4 curves. And here are the 2 papers where you can look further if you are interested in this. Both of these papers appeared in arXiv relatively, I mean, little bit like within like 2 weeks or something. So you can figure it out. You can look at it and figure it out if you are interested in this. Okay. Thank you so much for listening to the talk. And thank you for the organizer for giving me the opportunity to speak here.
Questions for
Fields which are not Q. Yes, we have. So in this paper for p isogenous case, we not only do it over Q, but we also do it over Q adjoint I and Q adjoint third root of unity. So there are some examples. There is an example section where we give a list, complete list for those fields as well. Yeah. Yeah. And this is not only for class number 1, this is in general, but in the where we talk about only p isogenous discriminant twins, in that have a kind of an algorithm. We give an algorithm in the paper where if you follow the algorithm, you can produce the whole list by yourself. Like it's computationally possible. And we give few examples. And I think one of the example is not class number 1. So there is example you can find in that paper. Like you can code the algorithm and find it out for any kind of number field you are working on. So it's pretty computable. It's not like the theory is just theoretical. You can compute it and you can get the list. Yeah.
Let's think Manami again.